Okay, so you've heard the story. Apple falls from tree. Newton gets bonked on the head. Newton invents gravity. That's the version everyone knows. That's the version that gets printed on motivational posters and told to kids in school to make science sound spontaneous and fun. Here's the thing though, it's not entirely wrong. There actually was an apple tree. Newton himself talked about it, but he didn't get hit on the head. That part got added later because a good story needs a physical comedy moment, apparently. And he didn't invent gravity, because gravity was already there doing its thing, whether Newton noticed it or not. What actually happened was more interesting and also more Isaac Newton. He was sitting in a garden, probably at his childhood home in Lincolnshire, England, probably in 1666, probably thinking about something extremely abstract. He watched an apple fall, and instead of thinking, oh, apple fell, that's a thing that happens, he thought something like, why does it fall straight down and not sideways? Why does it fall toward the center of the earth specifically? What if that same force, whatever it is, extends further than just apples? What if it extends all the way to the moon? That last question, that's the one that changed everything. Because once you ask that question seriously, once you actually sit down and do the mathematics, you end up deriving one of the most powerful descriptions of physical reality ever written by a human mind. That's Isaac Newton. He didn't just notice things. He asked why, and then he had the mathematical ability to actually answer. Pull up a chair. We're going to talk about one of the strangest, most brilliant, most contradictory people in the history of human thought. Chapter 1, A Difficult Beginning. Isaac Newton was born on January 4th, 1643, in Woolsthorpe by Colsterworth, Lincolnshire, England. And he almost didn't make it. He was born prematurely, so small, according to family accounts, that he could fit inside a quart pot. His mother later told him that when he was born, he was so tiny they didn't expect him to survive the first day. To women sent to fetch medicine from a neighbouring house, apparently sat down on the road on the way back, fully expecting the baby to be dead before they returned. He was not dead. Newton, as would become a pattern, refused to do what was expected. His father, also named Isaac Newton, which was either a lovely tribute or a deeply confusing household. Situation had died 3 months before Isaac was born. So Isaac came into the world already fatherless, already fragile, already behind. Then, when he was 3 years old, his mother Hannah did something that shaped Isaac's psychology for the rest of his life. She remarried. Her new husband was a wealthy clergyman named Barnabas Smith. Smith did not want Isaac as part of the new household. So Hannah moved in with her new husband and left young Isaac behind to be raised by his maternal grandmother. Let that sit for a second. His mother left him. Not forever. Not completely. She was in the same village, but she moved out of the house when he was 3 and didn't come back for about 8 years. Young Isaac grew up watching his mother go home to a different house, to a different family, to a man who had explicitly excluded him. If you're looking for the root of Newton's profound difficulty with human relationships, his lifelong tendency toward isolation, his explosive anger when he felt threatened, his near-complete inability to form close bonds with other people, It probably starts here, in a farmhouse in Lincolnshire, with a 3-year-old boy watching his mother walk away. He reportedly once, in a moment of childish rage, threatened to burn down his mother's house with her and her new husband inside, which is the kind of thing a deeply hurt kid says. He later wrote it down in a list of his sins, feeling guilty about it as an adult. He felt guilty about a lot of things. Newton's grandmother raised him reasonably well, and when his stepfather died and his mother came back with 3 new half-siblings, Isaac was apparently not thrilled about any of this. He was around 11. He had been essentially alone, emotionally speaking, for 8 years. Coming back into a busy family household was not what he wanted. What he wanted, apparently, was to be left alone with his thoughts, which was basically all he would ever want. He was sent to school in Grantham, the nearest town of any significance. He boarded with a local apothecary, a druggist, essentially named Mr. Clark, and it was there, in the Clark household, around books and chemical equipment and the general atmosphere of a man who dealt in knowledge. That's something in young Isaac started to wake up. He was not initially a spectacular student. He was described as inattentive, not particularly impressive. But at some point something clicked. He started paying attention. He started not just doing schoolwork, but consuming everything he could find to read. He built models, mechanical windmills, sundials, things that required understanding how things worked. He was particularly fascinated by how things worked. The local schoolmaster eventually told his mother that Isaac was too gifted to be a farmer, which was what she'd been planning. He needed to go to university. Hannah Newton agreed. In June 1661, Isaac Newton arrived at Trinity College, Cambridge. He was 18 years old and had essentially never had a real friend. That would not improve significantly. Chapter 2, Cambridge and the Making of a Mind. Cambridge in 1661 was not the gleaming institution of intellectual excellence. You might imagine it was, honestly, a bit of a mess. The official curriculum was still largely based on Aristotelian philosophy, a system of thought that was, by the 1660s, increasingly being shown to be wrong about a lot of things. The actual cutting-edge science and mathematics happening in Europe, Galileo's work on motion, Descartes' analytical geometry, the new astronomical models, wasn't part of the standard teaching. Newton arrived as a subsizer, which meant he was essentially a working student, performing menial tasks for wealthier students in exchange for his keep. This was not a prestigious position. It would have been socially awkward and probably humiliating in the class-conscious world of 17th century England. Newton seems to have responded to this the way he responded to most social difficulties, by ignoring the social world almost entirely and burying himself in books. He kept a notebook. He called it his waste book, which is a very Newton name for what turned out to be the most important notebook in the history of science. And in it he wrote down everything he was learning, thinking, questioning. He started with the standard curriculum and then blew past it, teaching himself from primary sources. Descartes, Kepler, Galileo, Wallis. He found a book on astrology at a county fair. Astrology was nonsense, obviously, but it required trigonometry, and Newton discovered he didn't know enough trigonometry. So he went and bought a book on trigonometry. The trigonometry book required Euclidean geometry. He got a book on that. and so on recursively, until he had essentially reconstructed the entire mathematical knowledge of his era, from first principles, in his spare time, while also technically enrolled in a degree program. He graduated in 1665. By that point, he had already, in his private notebooks, extended mathematical knowledge significantly beyond what any of his teachers knew. He had developed early versions of what would become calculus. He had started thinking seriously about optics. He had notes on the nature of forces. None of this was turned in as coursework. He was just doing it for himself because the questions interested him. Then the plague hit. The bubonic plague, the Black Death, swept through England in 1665 and 1666. Cambridge was shut down as a precautionary measure. Students were sent home. Newton went back to Woolsthorpe, and there, in about 18 months on a country farm, he laid the foundations for three of the greatest scientific achievements in history. Chapter 3. The Miracle Years minus 1665 to 1666. These 18 months have a name in the history of science. They're called Newton's Annus Mirabilis, his miracle year, or miracle years. What happened during this period is almost genuinely hard to believe. First, mathematics. Newton, stuck at home with nothing to do except think, developed the method of fluxions. This is what we now call calculus, the mathematical framework for dealing with rates of change, with curves, with areas under curves, with the mathematics of motion. He basically invented calculus from scratch, working alone in a farmhouse. Gottfried Leibniz Hammertischen would independently develop his own version of calculus about a decade later, which would lead to one of the ugliest priority disputes in the history of science. We'll get to that. Second, optics. Newton bought a prism at the Stourbridge Fair. Apparently prisms were sold as novelty toys at fairs in 17th century England, which is a delightful detail, and started experimenting with light. He made a small hole in his window shutter, let a beam of sunlight in, and passed it through the prism. The light spread into a rainbow spectrum. Everyone knew that prisms added colour to light. That was the received wisdom. The prism was somehow creating the colours. Newton didn't believe that. He passed the spectrum through a second prism and found that it recombined into white light. The colours weren't being added by the prism. They were already there in the white light, mixed together. The prism was separating them. He had discovered that white light is a mixture of all colours. This is foundational to our understanding of optics, of colour, of the nature of light. Newton figured it out in a farmhouse with a toy from a fair. Third, gravity. This is the apple tree chapter. Standing in the garden, watching things fall, asking why. Developing the hypothesis that the force pulling apples down might be the same force keeping the moon in orbit. Working through the mathematics. The key insight was the inverse square law. Newton worked out, through the mathematics, that if gravitational force decreases with the square of the distance, double the distance, 1/4 the force, triple the distance, 1/9 the force, then you could predict orbital motion. You could calculate exactly how the moon should move. And it matched. The numbers worked. The same force that pulled the apple was pulling the moon. He had unified terrestrial and celestial mechanics. the physics of Earth and the physics of the heavens, in a single mathematical framework. He was 23 years old. He didn't publish any of this for years. That's the thing about Newton that drives historians of science absolutely crazy. He had this habit of figuring out something world-altering, writing it down in his notebooks, and then not telling anyone. He had some deep reluctance about putting his ideas out into the world. Maybe it was perfectionism. He wanted everything complete before sharing. Maybe it was fear of criticism. Maybe it was just that the work satisfied him internally and the external recognition felt beside the point. Whatever the reason, most of what happened in Woolsthorpe in 1665 to 66 sat in private notebooks for 2 decades before the world found out. Chapter 4. Back to Cambridge. Professor Newton. Newton returned to Cambridge in 1667 and got a fellowship at Trinity College. In 1669, at the genuinely remarkable age of 26, he was appointed Lucasian Professor of Mathematics, one of the most prestigious academic chairs in England. His predecessor, Isaac Barrow, had essentially given up the chair so Newton could have it. Barrow recognized that his student had already surpassed him completely. As Lucasian professor, Newton was required to give lectures. He gave them. Students were supposed to attend. Often, apparently, nobody came. Newton would lecture to an empty room and then walk out after a set period. This might sound sad. Newton seems to have been fine with it. He wasn't teaching for the students. He was teaching because it was required. The thinking he did alone was what mattered. During the late 1660s and early 1670s, Newton continued his work on optics, eventually constructing a new kind of telescope. The problem with existing telescopes was chromatic aberration. The lens bent, different colours of light at slightly different angles, causing blurry, coloured fringes around everything you looked at. Newton's solution was to skip lenses entirely and use a curved mirror instead. The reflecting telescope. He built one himself, ground the mirror himself. By hand, it was small, but it worked better than much larger refractor telescopes of the time. When he showed it to the Royal Society in London in 1671, they were amazed. They elected him a Fellow immediately, a significant honour for a 28-year-old from Cambridge. Newton was pleased by this. He was even, briefly, willing to engage with the wider scientific community. He submitted a paper on his theory of light and colours, and then Robert Hooke attacked it. Robert Hooke was a brilliant, difficult, combative man who was one of the most important scientists of the era. He was also someone who had his own theory of light, and Newton's paper challenged it. Hooke wrote a critical response that was, by academic standards, fairly aggressive. Newton lost his mind. He wrote a furious reply. Then he withdrew from the Royal Society's correspondence almost entirely. He told his friend, Henry Oldenburg, that he regretted ever sharing anything. He went back to Cambridge, to his rooms, to his notebooks, and essentially disappeared from public scientific life for years. This would become a pattern. Newton could not handle criticism, not because he was fragile in a general sense. He was physically tough and mentally ferocious, but because his work was so deeply personal, so completely fused with his identity, that attacking his ideas felt like attacking him. He took every intellectual challenge as a personal assault. It made him almost impossible to work with. It also, weirdly, contributed to his genius. The isolation meant no distractions, no collaboration diluting the purity of his thinking. Just Newton, alone, pushing further than anyone else during these years. Newton was also doing something that nobody knew about and that would have seriously alarmed his colleagues if they had. He was doing alchemy, enormous quantities of alchemy. Chapter 5, The Secret Alchemist. Here is something the motivational posters don't mention. Isaac Newton, the founder of modern physics. The man who described the mathematical structure of the universe, spent more time on alchemy than he spent on what we now call science. He had over 1 million words of alchemical notes. He owned one of the largest collections of alchemical books in England. He ran his own alchemical laboratory in the garden of his Cambridge rooms, working late into the night, watching fires under crucibles, recording observations in his cramped handwriting. He was trying to turn base metals into gold, or more accurately, because Newton was not a simple man. He was trying to understand the secret structure of matter. He believed, as many serious thinkers of his era did, that ancient texts contained hidden truths about the nature of reality. He believed that the alchemical tradition, deciphered correctly, could reveal something about how matter was fundamentally organized at levels too small to see. He wasn't entirely wrong in his intuition. Actually, the alchemical tradition, for all its mystical baggage, was doing something that would eventually become chemistry. Newton's obsession with the hidden properties of matter was a precursor to atomic theory, even if his methods were pre-scientific. But the alchemy never produced its promised results. He never transmuted anything. He never found the philosopher's stone. He also, and this is important, may have been poisoning himself throughout this period. Mercury was central to many alchemical procedures. Lead, arsenic, antimony, heavy metals that are profoundly toxic. Newton handled these substances constantly, often without protection, often in enclosed spaces. Analysis of Newton's hair after his death found extraordinarily high levels of mercury and lead. This probably explains some things about Newton's personality and health in his later years. As we'll get to, what the alchemy tells us is that Newton was not the cool, rational, purely empirical scientist of popular imagination. He was a man of his era, the 17th century, a time when the boundary between science and mysticism had not yet been clearly drawn. He was simultaneously doing things that were foundational to modern physics and things that were rooted in ancient mysticism. He saw no contradiction because for him they were all part of the same project, understanding the hidden structure of reality. He was strange, magnificently, productively strange. Chapter 6, Halley's Comet and the book that changed everything. In 1684, a young astronomer named Edmund Halley, yes, that Halley, the comet he came to visit Newton in Cambridge. Halley had been having a debate with Robert Hooke and Christopher Wren about whether the inverse square law of gravity could explain planetary orbits mathematically. They were fairly sure it could, intuitively, but none of them could prove it. Hooke claimed he had a proof, but was being mysterious about it. Wren offered a prize of a 40-shilling book to whoever could demonstrate it properly. Halley decided to just go ask Newton. He asked Newton what curve a planet would trace if the gravitational force decreased with the square of the distance. Newton, without looking anything up, said, An ellipse? Halley asked how he knew. Newton said he'd calculated it years ago. He went to look for the papers. Couldn't find them immediately. Promised to redo the calculation and send it to Halley. A few months later, a 9-page paper arrived in London. It was called De Moto Corporum in Girum. On the motion of bodies in orbit, it proved exactly what Halley had asked about, and then substantially more. Halley read it and understood immediately that he was holding something completely extraordinary. He went back to Cambridge at his own expense and spent considerable energy convincing Newton to expand this work into a full book. This was not easy. Newton was reluctant, as always, to publish. He was also, at this point, engaged in a bitter feud with Robert Hooke, who was claiming that the inverse square law had been his idea first, and that Newton had stolen it. The feud was so intense that Newton threatened to withdraw the third section of the book entirely rather than give Hooke any satisfaction. Halley, who was simultaneously funding the book's publication out of his own pocket. The Royal Society had spent its budget on a book about fish, managing Newton's ego and editing the manuscript, performed one of the great acts of scientific diplomacy in history. He kept Newton publishing. He kept the project moving. In 1687, the Philosophiae Naturalis Principia Mathematica was published. The mathematical principles of natural philosophy. Principia. It is, without serious argument, one of the greatest books ever written. Chapter 7, what the Principia actually says. Let's talk about what Newton actually did in the Principia, because it's easy to say he described gravity and not really appreciate the scale of what that means. Before the Principia, here's how things stood. Astronomers had good descriptions of how planets moved. Kepler had established his 3 laws of planetary motion. Planets move in ellipses. They sweep equal areas in equal times. And the square of the orbital period is proportional to the cube of the orbital distance. These were accurate empirical descriptions. But nobody knew why. Nobody had a mechanism. Meanwhile, back on Earth, Galileo had done great work on how objects fall and move. He knew that falling objects accelerate at a constant rate, that projectiles follow curved paths. But the mathematics to connect this to anything bigger was missing. Newton connected everything. His 3 laws of motion, laid out in the Principia, are foundational. The first law, an object at rest stays at rest, and an object in motion stays in motion, in a straight line at constant speed, unless acted upon by an external force. This is the law of inertia. It sounds obvious now. In Newton's era, it was revolutionary, because the intuitive sense was that things naturally come to rest. You have to keep pushing them to keep them going. Newton said no. Motion is the natural state. It's stopping that requires explanation. The second law, force equals mass times acceleration. F. ma. Probably the most important equation in classical physics. It gives you the precise mathematical relationship between a force, the mass it's acting on, and the resulting acceleration. Every engineering calculation involving forces starts here. The third law. For every action, there is an equal and opposite reaction. Push on something, and it pushes back on you with the same force. Rockets work because of Newton's third law. You push gas out the back, the gas pushes the rocket forward. And then the law of universal gravitation. Every object with mass attracts every other object with mass. With a force, proportional to the product of their masses, and inversely proportional to the square of the distance between them. Every object, universal, not just Earth, not just the solar system. Every single thing with mass in the universe pulls on every other thing with mass. With this one law, Newton explained why apples fall to the ground, why the moon orbits the Earth, why the planets orbit the sun in ellipses, and proved it mathematically, why the tides rise and fall the moon's gravity pulling on Earth's oceans, why comets follow the paths they follow, the precession of the equinoxes. He did all of this in one book, using one mathematical framework in one unified theory. The Principia created classical mechanics. It was the foundation of physics for over 200 years, essentially until Einstein came along in the early 20th century and showed where Newton's framework needed modification. And even then, for everything moving significantly slower than the speed of light. At scales from the human to the astronomical, Newton's laws are still what we use. The calculations that got Apollo 11 to the moon used Newton's equations. The GPS system in your phone uses corrections based on both Newton and Einstein. At everyday scales, Newton is still running the show. He wrote a second edition in 1713 and a third in 1726. The year before his death, he was never entirely satisfied with it. He kept finding things he wanted to refine. Chapter 8, London, Politics and the Mint. Newton was not just a scientist locked in an ivory tower. He had, somewhat unexpectedly, a political life. In 1687, the same year the Principia was published, King James tried to appoint a Catholic monk to a position at Cambridge, without going through the proper academic procedures. Cambridge, which was an institution of the Church of England, resisted. Newton was one of the delegates, sent to stand before the royal, judge and defend the university's right to its own procedures. He stood firm. The judge threatened them. Newton didn't budge. James II was soon after overthrown in the Glorious Revolution of 1688. William of Orange came to the English throne. The political climate changed. Newton was elected as one of Cambridge's 2 representatives in the new Parliament. He didn't do much in Parliament. There is a famous story, probably apocryphal but very in character, that his only recorded speech during his time in Parliament was to ask a doorman to close a window because of a draft. But the political connections he made during this period opened doors. He was getting tired of Cambridge. The isolation that had once been productive was starting to feel like just isolation. He wanted to be in London, near the centres of power and intellectual life. In 1696, he got what he wanted. He was appointed warden of the Royal Mint. This might sound like a sinecure, a cushy honorary position for a famous scientist. Newton treated it like a war. The British economy was in serious trouble. The silver currency had been clipped. People were shaving small amounts of silver off the edges of coins, which debased the currency and caused inflation. The solution was a massive recoinage, essentially replacing all the old coins with new ones that had milled. Edges with ridges, which made it obvious if anyone tried to clip them. This was a logistical nightmare. Newton threw himself into it with the same obsessive intensity he brought to everything. He reorganized the mint's operations, increased production dramatically, oversaw the recoinage personally. He also hunted counterfeiters. This is one of the genuinely underrated chapters of Newton's life. He didn't just sit behind a desk at the Mint, he went undercover in London's taverns and criminal neighbourhoods, gathering intelligence on the counterfeiting networks. He personally investigated dozens of cases. He gathered evidence. He organised prosecutions. And he was ruthless about it. Counterfeiting was a capital offence, punishable by death, and Newton made sure it stayed that way. He successfully prosecuted a significant number of counterfeiters, including several who were executed. The most famous case was William Shalona, a skilled counterfeiter who had actually managed to embarrass the Mint and nearly get Newton removed from his position. Newton spent years building a case against Shalona, patiently gathering evidence from informants, and finally brought him to trial and had him hanged at Tyburn in 1699. Isaac Newton, reclusive genius mathematician, personally sent people to the gallows. He was promoted to Master of the Mint in 1699, a position he held until his death. He was very good at it. Chapter 9. The Royal Society and the Calculus War. In 1703, Robert Hooke died. Almost immediately, Newton became president of the Royal Society. Make of that timing what you will. Newton had refused to publish his work on optics while Hooke was alive, partly because Hooke had a competing theory of light, and Newton didn't want the conflict. The moment Hooke was gone, Newton published the Optics in 1704. The Optics is interesting because it's written differently from the Principia. The Principia is dense, geometrical, almost deliberately difficult to read. The Optics is much more accessible. It describes experiments, shows observations, and builds arguments in a way that educated non-mathematicians could follow. It was genuinely popular in the 18th century, read by people who found the Principia impenetrable. In the Optics, Newton laid out his work on light, colour, and the nature of white light. He also, in the later editions, included a series of queries, questions he posed at the end, about the nature of light, matter, and forces. These queries are fascinating because they show Newton at his most speculative, asking questions that he knew he couldn't yet answer mathematically. Some of them are surprisingly modern in their intuitions. As president of the Royal Society, Newton was not exactly a democratic or consensus-driven leader. He ran the place like a personal fiefdom. He controlled who got space in the Society's journal. He organised investigations that worked to benefit his own interests. He was, by most accounts, an extremely difficult person to deal with professionally. Which brings us to Leibniz. Gottfried Wilhelm Leibniz was a German philosopher and mathematician who independently developed calculus in the 1670s, after Newton had done so in the 1660s. But before Newton had published anything, Leibniz published first. Newton published later. Who should get credit? The answer, by all reasonable historical standards, is both of them. Independent discovery happens in science. Newton got there first chronologically. Leibniz published first. Leibniz's notation, the way he wrote calculus, is actually the notation we still use today. They both deserve enormous credit. Newton did not see it this way. Newton organised a committee of the Royal Society to investigate the question of priority. The committee's report concluded that Newton had priority. This sounds reasonable until you discover that Newton himself wrote the committee's report. He was literally judge, jury, and author in his own case. The dispute was ugly, personal, and dragged on 4 years. It poisoned the relationship between British and continental mathematics for decades. British mathematicians, loyal to Newton, stuck with his notation and methods, while continental mathematicians used Leibniz's better system, and British mathematics fell behind as a result. Newton never forgave Leibniz. Leibniz died in 1716, and Newton reportedly said that it had given him great satisfaction to break Leibniz's heart. This is not a great look. Newton was capable of extraordinary pettiness and vindictiveness in intellectual disputes. The greatness of the work does not require us to pretend he was a good person to his colleagues. He wasn't consistently. Chapter 10. The Religious Newton, the Secret Heretic. Here's another thing the motivational posters leave out. Newton spent an enormous amount of time on theology. He wrote about 1.3 million words on religious subjects, more than he wrote on mathematics and physics combined. This work was kept secret for most of his life, and only fully understood by scholars in the 20th century. What it reveals is that Newton held beliefs that would have been seriously dangerous to make public in 17th and 18th century England. Newton was an Arian. He did not believe in the Trinity, the Christian doctrine that God, Jesus, and the Holy Spirit are 3 persons of one substance. He believed that Jesus was a created being subordinate to God the Father. He believed that the Council of Nicaea in 325 AD had corrupted Christianity by inserting the Trinitarian doctrine. This was heresy, not mild heresious. If Newton had made these views public, he would have been stripped of his university position, which required him to be a member of the Church of England, possibly prosecuted, certainly professionally destroyed. He never made them public. He held Lucasian professorship that nominally required ordination as an Anglican priest. He received a special royal exemption from ordination, which was understood to be because of his scientific work. The real reason, which Newton never stated, was that he couldn't in good conscience be ordained into a church whose core doctrine he believed to be false. Newton was also deeply interested in biblical prophecy, particularly the books of Daniel and Revelation. He wrote extensive commentaries on these texts, trying to decode their symbolic language. He believed they contained real information about the future. He calculated, based on his interpretation of Daniel, that the world would not end before 2060. He was explicit that this was a minimum, not a prediction. He was trying to refute people who predicted imminent apocalypse in his own era, not trying to set a date. He believed that the universe was not running on its own. He believed that God actively intervened to maintain the order of things, that the stability of planetary orbits, which Newton knew had certain theoretical vulnerabilities over very long timescales, required periodic divine adjustment. This is philosophically interesting. The man who gave science its most powerful tool for explaining the world without recourse to the divine was, personally, deeply convinced that God was behind everything and actively maintaining it. Newton never resolved this tension. He didn't try to. For him, science and theology were both modes of access to truth. The universe was God's creation. Understanding the universe was understanding God's mind. The mathematics was a form of revelation. Chapter and your low Manfred and last years. By the early 18th century, Newton was famous in a way that very few scientists have ever been. The Principia had been out for decades and had transformed physics and astronomy. The optics had made him accessible to a broader audience. Voltaire had visited England, met Newton, and came home to France singing his praises to European intellectual society. Being a Newtonian, accepting Newton's framework for the universe became the marker of being an enlightened, rational modern thinker. Newton was knighted in 1705 by Queen Anne, the first scientist to be knighted in England for scientific work. Sir Isaac Newton. He was an old man by now, but he was still the most famous intellectual in Britain. He received visitors, corresponded with scientists across Europe, presided over the Royal Society with absolute authority. He also, finally, seemed to relax slightly. Had a niece, Catherine Barden, who lived with him in London and managed his household. By all accounts, she was charming and witty, and provided the warm domestic environment that Newton had never had before. He seems to have been genuinely fond of her. It's one of the few relationships in his adult life that seemed uncomplicated and affectionate. He drank only rarely, never more than moderately. He ate simply. He slept little. He had basically no interest in entertainment, theatre, music, art, or left him cold. He thought poetry was a kind of ingenious nonsense. He couldn't tell one musical piece from another. He had, late in life, one romantic attachment, probably. There's evidence of a relationship with a young Swiss mathematician named Nicolas Fatio de Dulier in the 1690s, which ended abruptly and seems to have caused Newton considerable distress. What the exact nature of this relationship was, historians can only speculate. Newton never discussed it openly. Newton began to decline physically in his later 70s. The mercury poisoning from decades of alchemical work was probably playing a role, though, of course, nobody knew that at the time. He had kidney stones. He had digestive problems. He occasionally became confused. He gave up his mint duties eventually, though he kept the title of master. He gave up the presidency of the Royal Society in 1725, when he was 82 years old. He had held it for 23 years. In early 1727, he became seriously ill. On March 20th, 1727, Isaac Newton died in his sleep. He was 84 years old. He had been born prematurely and not expected to survive the first day. He had outlived nearly everyone he knew by decades. He died unmarried, with no children, having lived alone for most of his life. He left an estate of around £32,000, a significant fortune, along with approximately 10 million words of manuscripts on mathematics, science, theology, alchemy, and history. He was buried in Westminster Abbey. Alexander Pope wrote the famous epitaph. Nature and nature's laws lay hid in night, God said. Let Newton be. And all was light. His pallbearers included dukes and earls. The French writer Voltaire, watching the funeral, reportedly said that Newton had been buried like a king who had done well by his subjects. Chapter 12. The legacy what Newton actually gave us. It's genuinely hard to overstate what Newton's work meant for the history of human civilization. Before Newton, the universe was mysterious. Things happened, and people observed them and described them. But the underlying machinery was opaque. Why did the planets move the way they moved? What held the cosmos together? What was light? These were open questions, and not even the framework for answering them existed. After Newton, it became thinkable, for the first time in human history, that the universe operated according to comprehensible, mathematical laws that applied everywhere, at all scales, for all time, not just the specific laws Newton had found, but the idea that such laws existed and could be found by human investigation. This idea that the universe is rationally ordered and mathematically accessible is the foundation of all modern science. Every physicist, chemist, biologist, engineer, and computer scientist working today is working within a framework of assumptions that Newton's work made possible. The direct applications are endless. Classical mechanics, all of engineering, from bridges to buildings to machines to vehicles, runs on Newton's laws. Every mechanical calculation, every structural analysis, every motion-related design problem starts with F equals ma, and the framework of Newtonian mechanics. Celestial mechanics. We can predict the positions of planets, moons, asteroids, and comets with extraordinary precision using Newton's laws. Space missions are planned using Newtonian mechanics, with Einsteinian corrections for high precision. The Voyager probes, launched in 1977, have traveled billions of miles through the outer solar system, and their trajectories were calculated using Newton's laws. They went where Newton said they'd go. Optics. Newton's work on light and color is foundational to our understanding of how we see, how cameras work, how telescopes work, how spectrometers work, how we know what distant stars are made of. Calculus, the mathematical framework Newton developed, is used in virtually every quantitative field of human endeavor. Physics, engineering, economics, biology, statistics, computer science. Calculus is the language they all speak. Every time you interact with software that uses optimization algorithms, every time a bank prices a financial derivative, every time a physicist calculates quantum mechanical probabilities, they're using tools that trace back to Newton's method of fluxions. The scientific method. Newton didn't invent the scientific method. Galileo and others had been developing it before him, but Newton's work demonstrated what the scientific method could achieve when applied rigorously. The Principia was the proof of concept for the entire Enlightenment project. Chapter 13. The weird stuff. Newton as a human being. Let's take a step back from the achievements and talk about Newton, the actual person. Because he was genuinely one of the strangest humans to have ever lived. He almost certainly had what we would now call autism spectrum disorder. The profile is almost textbook. Profound difficulty with social interaction. Intense and exclusive focus on narrow topics of interest. Extreme sensitivity to criticism. Rigid adherence to routines. Literal interpretation of language. Difficulty understanding social cues. Preference for solitary work. Exceptional ability to focus for extraordinary lengths of time on problems that interest him. He had, by all accounts, essentially no social graces. He could be rude without realizing it. He could be incredibly kind to people he liked and absolutely brutal to people who got in his way. He was intensely private. He didn't understand why anyone would want to know about his personal life. He forgot to eat. Not occasionally, regularly. He would get so absorbed in a problem that he would simply not notice that it was mealtime. His servant would bring food and come back hours later to find it untouched, and Newton still at his desk. He sometimes forgot to eat for entire days. He had almost no sense of humour. Contemporary accounts describe him as rarely laughing. He didn't find jokes funny in the way other people did. He was obsessively tidy about his work and his laboratory, but apparently not about everything else. His rooms were described as comfortable, but not particularly neat outside of his work areas. He slept 4 or 5 hours a night for most of his working life and considered this entirely normal. He had the social life of an isolated monk, and he seems to have been entirely satisfied with this arrangement for most of his life. Here's the thing though, these traits that made him difficult as a person were precisely the traits that made him scientifically extraordinary. The ability to focus obsessively and exclusively on a problem. The inability to be satisfied with approximate answers. The refusal to accept received wisdom just because everybody believed it. The social indifference that meant he didn't need external validation to keep working in isolation 4 years on problems nobody else was even asking yet. You can't separate the genius from the strangeness. They came from the same place. Newton himself, near the end of his life, reportedly said, "I do not know what I may appear to the world, but to myself I seem to have been only a boy playing on the seashore, and diverting myself in now and then finding a smoother pebble, or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me. It's one of the most beautiful things any scientist has ever said, and also very Newton, because even in expressing humility, he's framing himself as uniquely positioned to see what others miss, a prettier shell than ordinary. He'd found a few of those. Yeah, Isaac Newton was born in a farmhouse in Lincolnshire in 1643, to a family of minor farmers, prematurely, without a father, abandoned in some deep emotional sense by his mother at the age of 3. He could have been a farmer. He probably should have been, by most measures of probability. Instead, he became the person who figured out how the universe works. He invented calculus. He described the nature of light. He formulated the law of universal gravitation. He created the framework of classical mechanics. He built the first practical reflecting telescope. He reformed the British currency. He prosecuted counterfeiters. He spent decades studying alchemy. He wrote more words about theology than about physics. He was a difficult man, prickly, vengeful, isolated, obsessive, almost incapable of normal human warmth. He died with few close friends and no family of his own. He also changed everything. The world before Newton was a different place, intellectually. The world after Newton has never been able to go back to not knowing what he found. Once you know that gravity follows an inverse square law, you can't unknow it. Once you have calculus, you can't do without it. Once you understand that white light is a mixture of colours, the rainbow means something different forever. The stuff he figured out in that farmhouse, in 1665-66, while the plague raged outside and Cambridge was shut down, and he was 23 years old and completely alone. That stuff still runs the world. Not metaphorically, literally, the calculations that run the GPS satellites, the structural engineering that holds up the buildings you're in, the orbital mechanics that keeps the International Space Station in orbit, The optics that built the lens on the camera that took the photo on your phone. Newton. Not bad for a sickly premature. Baby from Lincolnshire, who wasn't expected to survive his first day. Not bad at all.